All right, welcome you guys. Today we are going to talk about how to graph polynomials. Now, when we graph them, we're kind of just loosely graphing them, we're sketching them. They're not going to be super precise, but precise enough really for even calculus. Okay, we don't have to get too detailed, just a general shape is really what we're looking for here. And we can get more detailed in calculus. A big section of calculus is curve sketching. And so you'll find intervals of increasing and decreasing, maximums and minimums, zeros, stuff like that. And so you'll be able to get really detailed in calculus. So here we're just giving a sketch. All right, so let's start off by defining what is a polynomial. So a polynomial is defined in the following way here. It says where the coefficients are real numbers and the exponents are whole numbers. So whole numbers are 0 and up. So just make sure that you know that. That's what the definition of a whole number is, 0 and up. Okay. All right. So what that means, let's give some examples of things that are polynomials and things that aren't. Okay. So I'll give you a few examples of polynomials. And then some examples of things that are not polynomials. Okay. All right, so some examples of polynomials. Okay. This would be an example. Okay. We have all real numbers as our coefficients, and all of the exponents are whole numbers. So if we keep track of the exponents here, this is really a 1. And if you want to think of this, this is really an x to the 0 right here. And so we actually have all 0 and up for the exponents. So this is an example. Another one, something you've been dealing with all class, a line is a polynomial. That's in y equals mx plus b form. So that would be a polynomial. And this, believe it or not, is a polynomial too. This always weirds people out. This is called the constant polynomial. Okay, you have to imagine that there's that x to the 0 behind it. So it really is going to be a polynomial. Okay. All right. Things that often students think are polynomials, but aren't. So say I have 3x cubed minus x to the negative second plus 2x. Okay. The reason why this is not a polynomial is because we cannot have negative exponents. We said 0 and up for the exponents. So that's the problem right there. Okay, another thing that would not be a polynomial, something like this. While the denominator is a polynomial, this whole thing is actually a rational function, right? The problem is we cannot have the polynomial in the denominator. Okay. If it is, then it becomes a rational function. Okay, so hopefully you have a good understanding of what is and what isn't a polynomial. Okay, so in this section, we're going to be concerned with the leading term a lot, but also it'll be nice for us to be able to speak the language. Okay, so we've already talked about how if we just have a number by itself with no variable, that's called the constant polynomial, and that its degree is 0 because you want to imagine an x to the 0 behind it. Okay, if the highest exponent is 1, which that's the case on this 2/3 x plus 5, then that will make a line when you graph it, and so we call it linear. You can see that it's in y, remember f of x is y equals mx plus b, so this will be a line. So you'll hear me use these words a lot: constant, linear, quadratic. So quadratic is when its highest exponent is 2, so degree 2 polynomial. Okay, and these kind of make sense. Cubic would be 3. Remember when we raise something to the 3rd power, we say we're cubing it. And quartic, like there's 4 quarters in a dollar, 4 quarters in a year. Okay, so this is the highest exponent of 4. And there's more. They go higher than that, but usually we just call it a polynomial beyond that. We're like, okay, 5 and up, polynomial. All right, now, when you have your polynomial written in descending order, like all of these are, right, from highest exponent to lowest, 4, 3, 2, 1, and none, okay? then the leading term is going to be the first term, the term of highest degree, okay? Might be written out of order sometimes, so you'll have to look for the highest degree or rewrite it, whatever you choose, okay? Now this is the leading term, and the numbers in front of the variables are called coefficients. So this is the leading coefficient, this -1. This is also a coefficient, -1.1, but it would not be the leading coefficient. It has to be the one in front of the term with the highest degree, okay? All right, so what we're going to do in these directions is we're going to find out what is the leading term, what is the leading coefficient, and what is the degree of the polynomial, and then we're going to name it, okay? All right, so it is written in descending order. So the leading term, I'm just going to put LT, you guys. The leading term is going to be 305x to the 4th. The leading coefficient, that's the number in front of the variable, so 305. And then the degree of the polynomial, well, it's a degree 4 polynomial. So since it's degree 4, it is going to be called a quartic. All right, let's go to this next one. So this one is not written in standard form in descending order, right? I would have to put the x to the second first, and then the x to the first, and then the constant. Or I'd have to have the quadratic term, the linear term, and the constant. Now I can see that the leading term for this polynomial is -1/2 x to the second. So its leading coefficient is -1/2, and its degree would be degree 2. And we know on polynomials like that, we use the quadratic formula because this is called a quadratic polynomial. Again, on C, h of x is not written in standard form or from highest exponent to lowest exponent. Now it is, we have our linear, our x to the first before our constant. So the leading term is actually going to be x. The leading coefficient is the number in front of x, which is a 1. And the degree is the exponent, which is going to be degree 1. So because of that, when we graph this, this would make a line, hence linear. Okay. So the reason why we're concerned with being able to find all of those pieces is that leading term actually tells us the end behavior of the graph. You can see that these pictures here, the middle is missing, and the middle's missing on all of them, right? It's basically saying what the right end is doing and what the left end is doing. What the right end is doing, what the left end is doing, okay? So the number in front, the leading coefficient, tells us what the right is doing. So you can see here, if the leading coefficient is positive, then the right-hand side's going up, and over here, the right-hand side's going up, okay? If the leading coefficient is negative, then the right-hand side's going down, the right-hand side's going down. So the positive or negative out front tells us what the right is doing. And you always have to find that first, because the left depends on the right. So you can't find the left first. You got to know, okay, what's the right doing? And then the left will either do the same or the opposite, okay? So I always tell people if it's odd, it's almost like the two O words were meant to go together, then the left will do the opposite. So you can see here, odd degrees, whatever the right is doing, the left's doing the opposite. The right is going up, the left is going down. The right is going down, the left is going up. So odd opposite. If it's even, then that implies that the left will do the same as the right. So if the right goes up, then the left will also go up. If the right goes down, then the left will also go down. So we will know just from that first term how both ends of the graph should look. Example 2, use the leading term to determine the end behavior of the graph of the function. Verify your answers with a graphing utility. Okay, so let's go ahead and go in here and figure out, well, what is the leading term, okay? So this one is written from highest exponent to lowest, so that front term is our leading term. So the leading coefficient is the number out front. Now remember, that number tells you what the right is doing, Okay, so the first thing I notice is that it's positive. So that implies that the right is going to go up. So maybe you could write right with an up arrow, however you want to look at it, okay? All right, now the degree. The degree of it would be 5 since that's the exponent. Now, we don't care about if it's positive or negative because remember, the degrees will never be negative. We said they have to be whole numbers. So what we care about here is the odd or the even. Since it's an odd number, that implies the opposite. So that implies that the left won't do the same as the right. Since the right went up, the left will go down. So this is going to be left down. All right. So if we were to kind of, sketch our polynomial, we don't know what the middle's doing, but we know that the right is going up and we know that the left is going down. We'll fill the middle in eventually. Let's go get an actual graph of this and then we can see what if we're right or not. Okay, so let me type in, we got x to the 5th minus 5x to the 3rd plus 4x. Okay, I think we did a pretty good job here because we can see that the right is going up and that the left is going down. I'm going to go ahead and get a little picture of this. Now they don't have arrows on it. You just have to know that it goes on forever. I'll put it right below it. So we can shrink it a little bit more. There we go. Okay. So if we put an arrow right here and an arrow right here, then you can see that it is doing what we guessed at. All right, let's try another one. So it is written in descending order. So the leading term is going to be that negative 2x to the 4th. So the leading coefficient will be negative 2. So since it's negative, that's going to imply that the right goes down. Okay. So right down. All right, let's look at the degree now. The degree is 4. That's the exponent, right? So degree 4, well, that's even. So that tells us that the left does the same. So the left will do what the right is doing. If the right's going down, then the left will also go down. Left, down. Okay. So if we were to sketch, I'll do it over here this time just so I can grab it and make a bigger picture. The right's going to go down and the left is also going to go down. Who knows what the middle does? Let's go and see. Okay, so let's just change this. So this is negative 2x to the 4th minus 8x plus 7. Okay, zoom out a little bit. Okay, interesting. Let me make this a little bit bigger. Well, there you go. So both the left and the right are going down. And weird stuff going on in the middle, huh? Find out more about that in a bit. There you go. So yep, we definitely go down to the right and down to the left if we were to fill ours in, right? Like that. All right. So this one is our first one that's been written out of order. So let's go ahead and rewrite h of x from highest exponent to lowest exponent. Now we can see that our leading term is negative 3x cubed. All right, so the leading coefficient is negative 3. So since it's negative, that tells us that the right is going to go down. So right down. Now our degree is degree 3. Probably bad examples, there's a lot of 3s going on, huh? So since that's odd, then that implies that the left will do the opposite. So if the right went down, then the left will go up. Left, up. So in a picture, the left goes up and the right goes down. Okay, let's go see what this one looks like. Okay, so this one is negative 3x to the third plus x, minus x, just kidding. And then plus 4. Okay. A little larger. Picture that there. And that is exactly what we said, right? We can see, we compare the two, right? That the right is going down and the left is going up. If we just went like this in the middle of ours, we would match. Remember, we're sketching, you guys. So that means that, loosely it looks like it. Okay. So now we're going to go ahead and pretty much for the rest of 4.1 talk about zeros. How do we find them? Is this number a zero? So remember that a 0 is an x value for which the y value is 0. In other words, it's a number c such that when you plug c into the function, you get 0 out. And because the y value is 0, you're on the x-axis, right? In this particular example, this one would be 2, 0. Notice the y value is 0. And in this particular one, it'd be negative 2, 0. So if we're on the x-axis, our y value is 0, making us an x-intercept, okay? All right, so let's go ahead and determine in example 3 whether or not these numbers are zeros. So if they are, when we plug them in, we should get 0 out. So let's go ahead and start by substituting in the 3, negative 3, just kidding. Remember, when you substitute in a negative, you must use parentheses, especially if you're doing it in a calculator. So you'll just see me always use parentheses when I'm substituting in, just to get you guys into the habit of doing that. Now from here, in my class, you know that you can just substitute this into a calculator, okay? Negative 3 times negative 3 times negative 3 is negative 27. Negative 3 times negative 3 is positive 9. Negative 5 times negative 3 is 15. And I like to finish this next line. I like to get all of my positives and all of my negatives, okay? Oops, this should be a positive right here, you guys. A negative times a negative equals a positive. Oof, caught my error. Okay, so what I mean by that is I'm going to go ahead and get the positives. So 18 plus 15 is 33, okay? And then I like to get my negatives. So 27 plus 6 is also 33, but this will be negative because they were both negatives. That's your 0, you guys. So it looks like this is indeed going to be 0. So our conclusion, negative 3 is a 0 of f. Boy, wish I, there we go. That's a little better. Okay, now let's just go to the calculator really quickly just to make sure that, we know how to use it. So parentheses, you basically plug it in just like it looks. Now this is the negative sign. In some calculators, if you use the minus, it'll say error. So make sure you can find the negative sign on your calculator. And then this is any exponent you want. You want exponent 3, just hit the right arrow to get out of it. All right, plus 2 parentheses, negative 3 parentheses. You can just hit squared here and it automatically gets out of it. You don't have to hit the right arrow. Minus 5 parentheses, negative 3, minus 6. Cool, it worked. All right. Let's go ahead and see if 4 is a 0. Now I don't technically need parentheses here because it's a positive number, but I told you guys just get in the habit of doing it. So that way you do it when you're using the calculator. All right, 4 times 4 times 4 is 64. 4 times 4 is 16. Now, I didn't talk about this last time, but I'll have a lot of students who will do 2 times 4 and then they'll square it. Remember, according to the order of operations, which we have this acronym PEMDAS, the E means exponents. Exponents have to come before multiplication. So you would be incorrect to do 2 times 4 and then do the exponent. You have to do the exponent and then the multiplication. So just a little thing there to make sure that you don't make some error, some syntax error. All right, so then 64, 2 times 16 is 32. Oops, what am I writing? All right, so 64 and 32 make 96. 20 and 6 make 26. So this looks like it would be 70. So our conclusion is 4 is not a 0 of f. Okay. And you can always go in and graph this, and we should be able to see if we were to graph it that that is the case. Okay, so let me delete this out. Switch this guy over. Let's put this in and see if this is the case. X to the third plus 2x to the second minus 5x minus 6. So you can see that -3 is a 0, right? It's an x-intercept. But when you come over here to 4, it does not cross, right, at 4. And that's why we got to know. It should be 70, right? Or if we go, when we look at this, 70. Yet when x is 4, y is all the way up here at 70. So it's definitely not a 0. All right. It's always good when it matches the picture. All right, so now we're going to find the zeros. So that's different, right? Different process. We're going to go ahead and let y be 0. So we're going to let f of x be 0. Because we said a 0 is when the y is 0. Now this is already factored for us. This is awesome. This is as good as it gets, right? So you would set each factor equal to 0. And then you would just move them over, getting the opposite signs, right? This one would be the same thing. This one will be -7. So we can see that we have x, 2 is a 0 with multiplicity 2. And then -7 is a 0. Okay, so those are going to be our zeros. Now we're going to talk later on about this multiplicity bit, so I'm just kind of foreshadowing it right now. If you just put down 2 and -7, that's all the answer is asking for. But let's go see what happens in the graph. We should cross at 2 and at -7. Put this in. 5x minus 2. Okay, so let's make this large. So we said that 2 was a 0, yes. And we said that -7 was a 0. And that is actually our only zeros here. Just put my tool on where I can shrink the y-axis so you can get a better picture here. There we go. Okay. All right. Okay, so this one is not factored for us, but you can see that we have 4 terms. 1, 2, 3, 4. And that is something we have been factoring a lot in this class. That's when we use factoring by grouping, right? We slice it down the middle. Remember y, f of x is 0. So from just these first 2, I can see that they have an x squared in common. So I'm going to take out an x squared, leaving me with just x minus 2. I have to take out a negative. Okay, that's a must. And it looks like I can take a 9 out of both 9 and 18. Now remember, when you take a negative out, the sign changes, and 9 goes into 18 2 times. And that is good news because we do want these to match, right? So we're going to factor the x minus 2 out, which will leave us with x squared minus 9. These will be the leftovers. The x squared minus 9 can factor further. It's a difference of squares. So we can factor it as x plus 3 and x minus 3. Now we're at the stage where we were on the last problem, where we just set each factor equal to 0. So we get x equals 2. X equals -3. And x equals 3. So that's going to be our zeros for this function. And I'm not sure how they have you put it in my math lab. I can't remember. They might make you write them as like ordered pairs. So I just want to mention this in case it does it this way. Okay. All right. So the next problem is very similar. So what I want you guys to do is try this one on your own. So pause the video, go in and see if you can do it, and then go ahead and hit play and see if we match. Okay. All right, so I'm going to slice it down the middle. It looks like we can take out an x squared again. I have to take out a negative, and 16 does go into 80. 16 goes into 80 5 times. And don't forget, we took out a negative, so the sign has to change. Plus, we know we want these to match, right? And so they do. And then the leftovers are x squared minus 16. And again, we have a difference of squares, which are my favorite things to factor. One's a plus, one's a minus, and just square root the last number, so 4. We set each piece equal to 0. We get positive 5, -4, and 4. And again, you could write those as ordered pairs. All right. Now this one's a little bit different. Okay, you're welcome to pause the video and try it on your own before me. That's always welcomed. So this one, it's going to factor in the usual, like where you draw the x and you look for factors of the last number. So things that multiply to make -45 and that add up to the middle number. So it looks like it's going to be what, 9 and 5 with a negative on the 5. So that way it adds up to +4. But the only difference from what we normally do, y is 0. Normally we would just be like, okay, x plus 9 and x minus 5, right? That's like what we would normally do. But I'm hoping that you can see that that is not going to be okay. Because when I start to FOIL this out, I'll get an x squared. But I'm supposed to get an x to the 4th, right? So the way to fix it is just put some squareds. Sorry, let me get rid of that arrow. The way to fix it is to just put some squareds on these guys. That works. That's when you multiply what's going to give you that x to the 4th now. And if you FOIL the whole thing out, you can check and see that indeed it does give me what we started with, okay? All right, and then something that I want to, make a note of. Neither one of these factors, okay? I have students who will try to factor it, but I want to just make sure that we understand why we can't, okay? So neither factor factors further. The problem with the first one is it's a plus sign, okay? Actually, so I'm just going to say can't have a plus. Oops. It's a difference of squares. That factors. Difference means minus. Means subtraction. Should probably put that. Okay, so if this were x squared minus 9, it would totally factor, right? If it were a minus, then it would be x plus 3, x minus 3. Okay, but x squared plus 9 does not factor, okay? All right, let's look at the second one and what's the problem with that one. So with the second one, the reason why that one doesn't factor, maybe you guessed it, since 5 is not a perfect square. Okay, if it were a 25, totally, right? If this were a 25, a 36, 16, 9, 4, 1, any perfect squares, cool. But you can't square root 5, so it won't factor, okay? So what that means is we're just going to go ahead and set each piece equal to 0 as they are. Okay, so we're not going to factor them. So we'll move the 9 over. And then we'll go ahead and square root, and nobody's going to forget their plus or minus is hopefully what you were saying. All right, now let's deal with the square root of -9. Remember from earlier in the class that a negative means there's an I, and you pull the negative out and make it an I. And then the square root of 9 is 3. So this is going to be plus or minus 3i for 2 of our solutions, right? 2 of our solutions. Let's do the same thing over here. Slightly different though. When we square root, we can't square root 5, so we just leave it. So that's going to be 2 of our other solutions. Now, something that I want to remind you guys of is to do an exponent count, right? The degree for this is a degree 3 polynomial, because x times x times x means x cubed. And we really did get 3 answers if you count the multiplicity, right? We got 2 twice, so that's 1, 2, and then -7 for 3. If you come over here, the highest exponent was 3. And notice we got 1, 2, 3 answers. So we found them all. This will help you make sure that you don't lose some along the way. This one was also degree 3 in the beginning, right? So degree 3. And so we ended up getting 3 answers here. This one's degree 4, and here's where you would really want to check, because a lot of students forget the plus or minus. Without the plus or minuses, you would have this, and you'd only have 2 solutions. So you would know you would be wrong, because the highest exponent is 4, so we should be getting 4 answers. And with the plus or minuses, we have 4. 3i, negative 3i, root 5, negative root 5. There's your 4. All right. Okay, so I knew that the multiplicity was coming, right? And so here we go. So the multiplicity, once you've factored your polynomial, you're just going to be looking at the exponent. That's going to tell you the multiplicity. If you go back to the one a second ago, it was this one right here. Another way that we could have written it is we could have, instead of x minus 2 and another x minus 2, we could have said x minus 2 squared. So that tells us, since the exponents are 2 and 1, that tells us the multiplicity on each. This one would be multiplicity 2, and this one would be multiplicity 1, okay? All right, now why do we care? Well, we're trying to fill out the middles of the graph. I mean, we know the end behavior now, but finding these zeros and their multiplicities are going to fill in that middle and tell us what the middle of the graph is doing. So the key thing is that if you have an odd exponent, an odd multiplicity, then you are going to cross the graph. Now, there's a couple ways it could cross. So let's say C is right here. It could just straight up cross, like it just passes right on through. Oops, I kind of missed. Let me see if I can actually hit it. And that would be degree 1. It could also cross in what we call a shelf point. So a shelf point, you know, maybe it's not arching this way, but that would be what we call a shelf point. And that would be degree, it's still odd. So like 3, 5, 7, 9, ... anything higher than 1. Okay. If the degree is even, if the multiplicity is even, then you will be tangent to the graph. So that means that if this is C, that you're not going to cross. That let's say you're heading down, then you're going to turn back around instead of actually crossing. Now it could be above it or below it. I don't want you guys to think these have to look this exact way, right? It could be that here's your C and you came up and you decided to turn around, but just make sure that you do not cross through. You just nick it. You're just tangent to it. Okay. All right. So let's go in here and look at these. So what effect do the multiplicities of the zeros have on the graph? Okay. All right. Well, what are the exponents is going to be our first question, right? Okay. Well, if there's nothing there, we know it's a 1. So since all of these are degree 1, they're all going to be crosses. Now let's go in and actually get the zeros. So if we set this one equal to 0, this one will be a cross. If we set this one equal to 0, we'll get +1. That would also be a cross because of its exponents, right? And then this one would be x equals -3, which would also be a cross. Okay. So you can see in the graph at -3, we just go right on through, we cross. At 0, we just go right on through, we cross. And at x equals 1, we cross. So we do have the right zeros, right? We got -3 on here. We've got 0 on here. And we've got 1 on here. All right. Let me just go in and clean up things. A better arrow. There we go. Okay. So we have the same exact zeros here. If we set each piece equal to 0, we'll get +1 here because we'd have to add the 1 over. And we'd get -3 here because we'd have to subtract the 3 over. But now the exponents have changed, right? The exponent is 1 here. That means it's going to be a cross. The exponent is 2 here. It will not cross. It'll be tangent. And the exponent is 1 here. So it'll be a cross. So let's go and check. Here we are at -3. Yes, we crossed through the x-axis right here at -3. Here is x equals 0. And yes, it's hard to see, but we crossed through at x equals 0. Now here at x equals 1, right? This is going to be the one for 1. Well, we did not cross. I didn't go from above the x-axis and pass through and go below it. I came from above and I stayed above. I turned around. So that's our tangent, right? So this one is the one that is tangent. Okay. Next one, same thing. We got the same zeros. Okay, let's see what our exponents look like. This one's a 1, so it's a cross since it's odd. This one's a 1, so it's a cross. And this one's a 2, so this one should be tangent. So let's see. At 0, did we cross? We sure did. We went through the x-axis. At 1, did we cross? Yes, we went through the x-axis. At -3, we did not cross. We came down and turned around. So we did not pass through the x-axis. So we are tangent there. So this one would be the tangent one. Okay. And this just says it again, right? If it's odd multiplicity, it crosses. If it's even multiplicity, it's tangent. Okay. So find the zeros of the function and their multiplicities. State whether the graph crosses or is tangent at each 0 and verify with the graphing utility. All right. So we're going to set each piece equal to 0 if we want to find the zeros, right? Make sure you let y be 0. Okay, so I'm going to set this piece equal to 0, which gets us 1. And then we'll set x plus 2 equal to 0, which gets us -2. Now, if we look at the exponents, right, of 1 and 2, so this one is going to be multiplicity 1, and this one is going to be multiplicity 2. So if it's 1, it's odd, so it crosses. And if it's 2, it's even, and so it's going to be tangent. Now, it does say to verify with a graphing utility. So let's go in here and use GeoGebra to see what happens on this graph. I'm probably going to go back to counting by integers. Not make that so small. Okay. All right. Switch this guy over. All right, so we got negative x minus 1, x plus 2 to the, okay. All right, so we said that at x equals 1, we should cross. Well, we do, we pass through the x-axis. Then we said at x equals -2, we should be tangent, and we did, we came down and we didn't cross through, we went back up again. So this definitely supports what we were saying. Let me kind of exaggerate the tangentness really quickly. There, now you can see it a little bit better before I take a picture of it. That looks great. Okay. Get some of these stray marks. I got left-handed issue. I guess everybody has to balance their hand though when they're writing on their tablets, but okay. All right, so this one is already factored also. You gotta love that. So we're gonna set x equal to 0. We're going to set x plus 4. Notice I don't carry the exponent with it. I'm just setting the terms, the factors, I'm sorry, equal to 0 without their exponents. Because if x is 0, when you square it, it'll still be 0, right? If x minus 7 is 0, well, when you cube it, it'll still be 0. So I'm ignoring the cubed, I didn't put it there. I'm ignoring the squared, I didn't put it there, right? All right, so this one's going to get me x equals -4. This one's going to get me x equals 7. And let's go in here and get the multiplicities, right? So the multiplicity, you got what, 2? Which implies tangent since it's even. We've got 1. So it's going to be across. And we've got 3. So it's going to be a cross, but if you remember, it's going to cross in a different way. It's going to cross as a shelf. Okay. So like if I were hand sketching this, it's going to go down to the right because the leading term is negative. And then let me get the zeros in here. So we'll just pretend this guy's 7. So 7, 0, and -4, right? Okay. So we said that, let me make this move over a little bit more. What happens at 7? We're going to have a shelf. So it should come up here, go like that. There's your shelf, right? That somebody could kind of, sorry, it's so shaky, you guys. All right, and then at 0, we're tangent. So when I come over here to 0, I'm going to come back up again. And then at -4, we cross. So maybe something like that. I don't know how high or how low this dips, you know? That's something that in calculus, we'll get the maxes and the mins on it. So it's really shaky. Sorry, guys. Let's get the actual real graph. That's way better than mine. All right. Okay, so we got -3x, x plus 4, and then x minus 7 to the third. Let's see what this guy looks like. Holy moly, I need to definitely zoom out, don't I? Super high. There we go. There's 7, 0, and 4. I should put this way too. Okay, what did I do wrong? Did I type this in right, you guys? Oops, I did not. There it is. This is to the second. Okay. Now we're in there. Okay. So let me snap a picture of this, or let me just pull back the other one real quickly so we can compare the two. Okay. So yes, I don't have the right heights. This one went a little higher, right? So in hindsight, this one was the higher one. But I told you guys, we don't really know who's higher and who's lower till we start finding maxes and mins, nor do I care really at this point. All right. Okay, so at -4, we cross through. At 0, we were tangent. And at 7, it crossed through, but it crosses through in this wiggling way where we make a shelf point. That's different than this cross through, right? Little man could stand on the graph, right? We could have somebody standing here. We could not have somebody standing on that. Okay. All right, let's take a picture of this and bring this to our screen. Okay. All right. Put in values for the exponents that could give you the given graph. So you can see that if we set these equal to 0, right? If we set x plus 3 equal to 0, we're going to get -3. And that's this one right here. -3 is a cross in the picture, right? This right here is a cross. So that implies that the exponent has to be odd, and it crosses where it's not a shelf. So the exponent would have to be 1. Okay. If we set the x minus 1 equal to 0, we get 1, which is exactly where this 0 is, right? So that one's a cross, but it's a cross that's a shelf, right? So that's going to imply odd, but it's going to imply odd where we use like 3, 5, 7, 9, whatever. We can't use 1, right? So let's say we put a 3 on it. So let's see how we did. X plus 3 to the first and x minus 1. X plus 3 to the first, and then x minus 1 to the third. And let's just make this more normal in size, not so zoomed out on the y-axis. And then let's count by integer values, not by twos. Okay, let's see how we did. Let's compare the two. Pretty darn good, right? So we said it's got the right shape, right? It passes through -3. And then, I mean, I could just drag this down more if I wanted to make it look more like it, right? Now you can see that it's pretty much matches it exactly. Okay. All right. Yeah, that's great. Really good, huh? Okay, pretty happy with that. All right, let's try the next one. Okay, so we can see that for x equals -3, it crosses. So we know it has to be odd, but it crosses as a shelf. So the exponent would have to be 3, 5, 7, 9, anything but 1, right? So let's say that we put a 3 in there. Okay. Then for the 0 of 1, this does not cross. This is actually tangent, right? So that implies that we have to have some sort of even exponent. So maybe a 2. I always just pick the smallest, you guys, if you're going, where are you getting these numbers? All right, so 3 and a 2. Let me go ahead and change the exponents to a 3. And then let's change this one to a 2. And let's see how we did. Okay, is that how it looked? Let me go back, pull it up. Oh yeah, that is good, right? Okay. It's a little bit bigger. And then let's hide this. Look at that, right? That's spectacular. Now, as far as I told you, I picked the smaller. I mean, what would happen if we changed it from a 2 to a 4? We picked some other even number. It's gonna have the same behavior. It might like go a little bit higher and stuff, but it's still going to, let me make this large, have the same behavior of being tangent at 1 and a shelf here, right? If I shrunk down, let me do it. Move this up a little bit. There we go. It's still going to look pretty much the same, you guys, if I shrink it down. You have that, tangent and then that shelf. Okay, so you can really pick any even value and I would give it to you. Okay, because then you understand that it has to be an even number if it's tangent. Okay. All right, so let's see here. -3 is a shelf, right? It crosses, but it crosses in a shelf. So that means odd, but odd like 3, 5, 7, 9, something like that. So we'll pick 3. And this one's also a shelf, right? So this one also crosses, so it's odd. But we can't use 1 because 1 crosses straight through. So we'd have to pick 3, 5, 7, whatever odd number. So let's say we pick 1. Okay. All right, you guys. So that is it for example 6. We're working our way into being able to graph some polynomials, and we have all of the pieces now. So we know what the right end is doing, what the left end is doing. We know where it crosses the x-axis at and how it behaves when it crosses that x-axis. So we've got the ends and the middle now. All right, thanks for joining me. Take care.